In this video, we solve problem 12.3.044 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're given the position vector, and we're told that it describes the path of an object in the xy plane, and we have that here. We're also given a location, an x and a y value, x equals 1, y equals 6. We're asked to find the velocity, speed, and acceleration of the object. The velocity is just the first derivative of position. I prefer to use component form, so I will write my vector this way. That's t times I hat plus negative t squared plus 7 times j hat. In component form, the velocity is written this way. We take the derivative of the first component and we get 1, and the derivative of the second component and we get negative 2t. The speed is the magnitude of that vector. So we take the components, we square them and add them and take the square root. So that gives us the square root of 1 plus 4t squared. That's a scalar function of t. And the acceleration vector is just the derivative of the velocity vector. Derivative of 1 is 0, the derivative of 2t is negative 2, so this is just negative 2 times j hat. Then we're asked to evaluate the velocity and acceleration vector at the given point. For a particular value of t that's actually given to us. And you notice that if t is equal to 1, x is equal to t, and y is equal to negative 1 squared plus 7, which is positive 6 there. So t equals 1 actually corresponds to this location. So evaluating the velocity vector and acceleration vector at this point is the same as evaluating the velocity and acceleration functions at t equals 1. So we plug in t equals 1, we get 1, negative 2 for our velocity vector and an acceleration of 0, negative 2, or those are the components anyway. This is 1 times I hat minus 2 times j hat, and this is 0 times I hat minus 2 times j hat. Okay, so now we are asked to graph the path and sketch the velocity and acceleration vectors at the location on the path. So in order to do that, I would take my function r of t, which is written this way, and I would identify my x of t and y of t. So there's x and y. And what I'd like to do from here is just eliminate the parameter. Well, that's actually pretty easy since x is just equal to t. Since x is equal to t, I can replace t with x here, and we'll have y equals negative x squared plus 7. So when x equals 0, y is equal to 7. When x equals plus or minus 1, y is equal to 6. And so on. X is equal to plus or minus 2. We're going to have 7 minus 4, which is 3. This is not to scale. And so on. So you're going to have a parabola that looks like this. I almost started to draw an arrow on there. I don't want to do that. As t increases, x increases. So the arrows should actually go in the opposite direction. Okay. So now we want to sketch our velocity vector, which was the vector with components 1 and negative 2, and our acceleration vector. At this location, x equals 1, y equals 6. So we just go straight down. That's our acceleration. We go down 2 units. That's a of 1. Now the velocity vector should be tangent to the curve, and it should go in the direction of motion, and it does. We should go 1 unit in the x direction from here, and then down 2 units in the y direction. That velocity at 1 looks like that. So for on WebAssign, we're looking for a parabola that crosses the y-axis at y equals 7, and we're looking for 2 vectors, a tangent vector with components 1 and negative 2 at the location x equals 1, y equals 6, and then an acceleration vector that points straight down and has a magnitude of 2.